Hello, everyone. Good morning. Anyone have any questions before we get cracking?
Hi, yes, I actually have a quick question if you don't mind answering this for me.
No problem.
So how does the lab participation grades work in an instant? Like, as in, I see that it's like 0 out of 100. Like, how does your grading scale work?
So it's kind of a weird thing. I explain it to some extent in the syllabus, but I think a lot of people don't get it. So what I have is an attendance grade that is 50% you being there for the actual lab by my discretion. In other words, if you come in and then go to breakout room and then leave like after 15, 20 minutes, then you haven't really been at the lab. So that's even if you get the lab finished. So that's 50% of your attendance. The other 50% of your attendance grade is you turning in a lab report on time. Once you do both of those, you'll get 100. That being said, I don't really grade it where I average up all those hundreds and fifties and zeros and stuff like that. What I really do is you're allowed to miss one class and you're allowed to turn in one lab late. If you miss a class twice, then you drop down to 90% of that lab grade for that portion. And if you turn in a lab late, you're twice, you drop it 10% again. So basically it's like 50 points for being there, 50 points for turning the lab in on time, but it doesn't happen. Nothing happens until the second time you've missed either one. That way each one becomes, instead of 50%, it comes 45 and 45 after you've done 2 of each, and then 40 and 40 after you've done 3 of each, and then 35 and 35 after you've done 4 of each, so on and so forth. Does that make sense?
Oh, yes, no, that definitely does. So on the last lab was kind of lengthy. So me and my group, we ended up running out of time. And so we finished it, and then I turned it in like I guess you can say after hours. But
Right.
I guess my attendance
it's not required to be turned in until the next day. I mean, the next week. So if you had a lab on Tuesday, it's supposed to be turned in by the beginning of lab on Tuesday, the following week.
Oh, the following week. Okay. Because I just,
so if you turn it in that way, it's no problem.
Okay, cool. I just been seeing that I've been receiving a 50 for the lab attendance. So I guess the other 50 is with the submission of the actual lab report, correct?
Exactly. I fill out 50 points of that the day of the lab just by seeing who's there and spends, a good fraction of the time there. And then when the beginning of lab starts next time, after I get you guys into your breakout rooms, I then go in and say, okay, what students all turned in their labs, they're going to get their other 50 now. If they don't have them turned in at that time, then they get just keep the 50 instead of the 100.
Oh, okay, perfect. Yeah, that makes sense. Thank you so much. I just seen 50s all on the grading scale. I was like, man, I'm already off to a rough start.
No, you're not. Like I said, those 50s should become hundreds by the time you turn in the next lab, unless, like I said, unless you just missed the lab, or I found some students were only there 18 minutes out of 3 hours, or out of 2 hours and 45 minutes. So I can't give you credit for being there that short a period of time, because it keeps track of not only when you log in, it says when you log in, when you log out, how long you were there, and then when you log in again, it shows me another one. So what I do is I go through that report each day and look and see each student, how long they spent cumulatively in the lab.
All right, that's perfect. Yeah, sweet. Thank you so much for answering that for me.
You're welcome. Anybody else have a question?
I have another class-related question. I don't know if this was, I forget if this was already answered, but for the midterm and the final, is there also practice tests that you make?
Yeah, there will be one. I always put it up about a week in advance. In fact, there'll be 2 for the midterm, because one is for you to get practice on using the lockdown browser, the Respondus browser, and you do that one just once, and it doesn't really count toward your percent, to your bonus points for practice tests, because I don't care about your grade or anything on that. I just want you to make sure you do that at least a week before the midterm, so you can make sure your Respondus browser works. And then the other one is one you can take a bunch of times, and it's not under respondus. As you can tell, respondus is going to take a while. You got to show your workspace. You got to hold up each piece of paper front and back, and you got to show an ID, show your face alongside it, a bunch of stuff like that. So I just want to make sure all that works for you. So I give you one that'll have the word respondus in it. That's a practice test. You take that once, and then you'll have another one just as a practice test.
Yeah, because the practice test definitely helped give me an idea what I need to expect for the test.
Yeah, and I love doing it because I give you credit for it. You solve a lot more physics problems than just doing the minimal homework that I require. So it's just good all the way around. And you're seeing the banks that I consistently use for the tests in midterm and final. I usually do at least 80% of the points on a test coming from those practice tests.
That'll be beginning of October, I'm guessing, right? Correct.
What's that? Without being what?
The midterm is in beginning of October, right?
Yes. Yeah. So far, we're on schedule for everything. I just got to remind myself putting it in my calendar what day I made tests. Someone asked about how many tests we're going to have. Every 2 chapters, we're going to have a test. Occasionally, I'll spread it to 3 chapters, but generally, it's every 2 chapters we'll have at least an online test, and then we have that big midterm and that big final. As well. So I think we end up with like 6 tests plus a midterm and final or something. So solve a bunch of physics problems. That's the only way to become good at physics. You really need to learn how to, read books and examples and try to figure out how they work, how you can figure out how to solve problems by reading those. That's a big goal for any college educated person. So that's part of the reason a lot of college is required for things that seem to not, jobs that seem to not need a college education. What they're wanting to see is, hey, what if I give you a white paper? Can you read that white paper and then implement whatever that white paper suggested? That's a key learning goal for everybody. So I do that. Luckily, I actually am one of the people that I try real hard to explain everything in great detail so that you know exactly the nuts and bolts of how stuff is done. Matthew, is that you? I think you got a speaker. I think you should unmute. There you go. Anyways, so last time, refresh my memory because I actually had a bunch of stuff going on this morning, so I didn't get to look back at our notes from what we did last time. I want to say that we did actually add some vectors, add a bunch of vectors and got a net vector. We did do that last time, right?
Yes, we did that.
Okay, yeah, because I was pretty sure we did. We ended up, with a vector in IJK notation, and then IJ notation, and then I converted it back to a magnitude and direction notation. I wanted to make sure I got that done. I was pretty confident I did, but like I said, I didn't get to look back at my notes from last time. That being said, I'm going to now show you one really good, robust projectile motion problem using vectors. And in reality, I will give you a general method, and then I'll give you a specific example using that general method. And from that, you'll make some sense. The single most important thing, I think, in this entire chapter is the figure on page, let's see where it is. I think it's page 63, maybe. 63, yeah. Page 63, figure 321. It basically shows a red ball and a yellow ball at exactly the same height initially. And then the red ball is dropped while the yellow ball is shot horizontally. And from that, it takes a series of photos like every 60th of a second or something like that. And you see that the dropping ball and the shooting ball maintain the same height at each instant in time. What that tells us is that when you solve a projectile motion problem, you can treat the vertical motion entirely separately from the horizontal motion. And in this chapter, we're not even dealing with air resistance. So really, that means you have no air resistance, no friction or anything on the horizontal motion. And you also don't have air resistance on the vertical motion, okay? So what I often tell students when they're trying to solve a physics problem that involves projectiles is what you're really solving is imagine an ideal world where the sun is really directly overhead so that shadows are literally directly under an object at all points in time. So when you fire a projectile, that shadow is going to travel at a constant velocity. And that constant velocity is the initial x component of the velocity that the object was shot with. That doesn't change at all. It just rides along, blah, 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 right? At the same time, the vertical motion is doing the exact same thing that we learned in in one-dimensional free fall. If I throw a ball up, it's going to go up and come straight back down. So if you had a series of lasers over here that all fired horizontally, they would leave something like a shadow, an absence of laser light, and that would actually follow the exact path of a ball thrown straight up with initial velocity equal to the velocity or the vertical component of velocity at launch. So that is really the crux of it. It's all about if they want to find out, how far it travels. Well, you got to figure out how long that vertical component of velocity will allow a ball to stay aloft. Once you've got that time, you multiply that time by that constant velocity the thing is going to the right or left with, which is the x component of velocity, and boom, you've got the range, which is how far the projectile is fired. If you want to know how high it's going to go, well, the vertical component of velocity starts off at whatever that is. It's usually v0 sine theta. And when that reaches 0, that's the amount of time elapsed for it to reach that max height. Then you can put that in the equation for basically a vertical ball thrown vertically upward and find out what that distance is. So with that in mind, those explanatory steps in mind, let me show you using vectors a really nice, neat way to write your projectile motion problems. Okay, so I'm going to turn on my document cam. Anybody have any questions before I do that? Y'all sort of understand what I'm saying about figure 321? I'm going to write that down up here too. Well, I'm going to write it just where y'all can't see it because I'm just special that way. All right. So the big deal is in 3 dimensions, we often point to a position vector. And that position vector is either x of t. Some people will use, I like x of t myself. I prefer to use that. But I often use r of t. And it just says, really, what is the vector that points to the particle that you're studying at any point in time t? In reality, it could actually depend on other variables, but we always do just time, okay? So what we know is that we can treat the horizontal motion entirely separately. So what we know is that the x, distance traveled, is equal to x0 plus v0 t. Really, that would be plus 1/2 a sub x t squared, but we're doing no air resistance, so this part is 0. The acceleration in the x direction is 0, and often we'll automatically just make the particle start at the origin. There's good reasons not to in many cases, but we can start at the origin, in which case that would be 0. So a simple case that starts at the origin, let's say like this. Okay, it's fired at some angle theta with some velocity v, and it's going to land some distance down the road at the same height. When you have that simple scenario, then you can just write, notice the x0 is now 0 because we started at the origin. The v0 is just going to be v0. I'm going to put the t here so it's not ambiguous as to whether the t is being having the sign taken of it. So v0 t times the sine of theta times I hat, and that's because we started at the origin. So we know this thing is just horizontal motion, the magnitude of the velocity being v0. Oh, that's a v0 sine. Sorry about that. Everybody catch that. I was thinking I was doing the y one and wrote sine instead of cosine. That's not good. Okay, so that's the horizontal motion. It just takes this particular component of velocity right there. That's the v0x. Now the y component is completely separate, and all you have to do is write parentheses, bracket. And now this time I'm also going to assume that the initial position is 0, because again, I started at the origin. So I'm going to say that is V0, which is what this velocity should be. I should have put a 0 on that as well. Okay, and actually I should make a vector symbol so we can see it's like this. So that V0 times t times the sine of theta. That's the V0t component from that typical equation, except you got to use the sine to get the vertical component. And then you have, because I'm going to call gravity pointing downward, we're going to, which is, I mean, gravity is obviously pointing downward, but because I've drawn my y coordinate vertically upward, then the g has to be negative. So I'm going to write -1/2 g t squared and put a j hat after it. And that's it. Okay. If you wanted to be more general, you could, for instance, do something like this. Call this x, call this y. Say you got some cliff right here. Say you're shooting the projectile like this. And then that's your position x0, y0. This is still your angle theta. And that's still your velocity v0 right there. Okay, that's a similar problem, only this time we're going to write r of t is equal to x0 plus v0t cosine theta I hat plus y0 plus v0 t sine theta minus 1/2 g t squared j hat. So if you want to find out, for instance, at a particular point in time, how far has the projectile moved in the x direction, you just put in t right there in this part, and this x coordinate will give it to you. Okay. If you want to find out how high it is at that time, well, you just read this part. If you want to find out, for instance, how far downfield it's going to go, you have to figure out how long it's going to take from for y to equal 0. Notice I put y0 was the initial one, so I have to set this entire thing equal to 0, solve for t, which I think you can tell is going to require you to use the quadratic formula, and then plug that time into x, and that'll give me where it landed downfield. Now you'd have to subtract x0 from it to find the actual range, but that works. Now the beauty of this is you can then, if you want to know specifics like how fast it is in time, well, you can do something like realizing that v of t is just dr over dt, in which case when I take the derivative of this, this just becomes v0 cosine theta times I hat, and immediately you see, oh yeah, the velocity is constant along the horizontal direction. And when you take this derivative, that's 0 plus v0, or excuse me, I'll just leave the plus off, v0 sine theta minus gt I hat. So that's the actual velocity vector. And finally, if you want to know the acceleration, which hopefully y'all know about this by now from chapter 2, but the acceleration is dv dt. Obviously, there's no t in there at all, so that's going to become 0. And in fact, all you get now is negative g j hat, and that's the fact. Once the projectile leaves the barrel of the gun or whatever, it's going to maintain a constant acceleration until the instant it actually hits the ground, and that acceleration is g in the downward direction. Okay. So let's solve an actual physical problem. I'm going to, first I'm going to make use of our special triangles. And I really like the 3, 4, 5. So I'm going to say the 4 is here, the 3 is here, and the 5 is here, in which case this is 53.1 degrees. It's actually 53.13 and some change, but that's close enough. Okay. So what I'm going to say is a projectile is fired from the top edge of a cliff at an angle of 53.1 degrees above horizontal. Okay. And at a speed of, let's say, I'm going to say 50 meters per second. Assume there is no air resistance and that the cliff is 100 point, so it's 3 sig figs tall. A, max height. B, time at max height. Okay. C, the range. And that's just the distance. In this case, I'm doing something just like this. My coordinate's going to be a little different, but just to show you what I mean, this is range. Okay. And this is H, the max height. Okay. And let's say D, final velocity. Okay. So I'm going to draw my coordinate system again. I don't really have to draw it that big, right? I just need to draw it. So I'm going to draw it right here like this. Draw an X there, draw a Y there. And we were at the, it's told it was fired at the edge of a cliff. So I'm going to make the edge of the cliff right there. This is going to be 100 meters. And this is going to be 53.1 degrees. And this velocity V0 has a magnitude of 50 meters per second. So what's going to happen is it's going to fire like that, reach some max height, and then land down here. So there's my R. There's H, my max height. And also T, MH is equal to question mark, question mark, question mark. And then finally, V final is equal to question mark. Okay, that is a vector quantity, so that's important. That's why I wanted to take the time to draw it with a vector symbol over it and all that good stuff. So from that, I can go ahead and set up my position vector. I know my position as a function of time is actually going to be, notice I put it at x equals 0 for my initial coordinate, but at y equal 100 meters. So in this case, it's just going to be V0, which is 50 meters per second, times the cosine of 53.1, but you can see the cosine of 53.1 is going to turn that 50 into 30. So it's going to be 30.0. I should put a 0 here too for sig fig reasons. 30.0 meters per second times t in the I hat direction. Okay. Plus, now I'm going to put 100.0 meters, and I'm putting that there just to remind me that all three of these digits are significant. The underlined ones aren't supposed to count. Okay. Plus, now when you take the sine of 53.1, you get 4/5, and that's going to turn the 50 into 40 meters per second. So 40.0 meters per second t minus 4.90 meters per second t squared, and that's in the j hat direction. Okay. I very seldom actually work vectors, work out a projectile motion problem keeping the vectors, but I'm doing so now just so you can see how you can. Sometimes it's really nice and it can make life a little simpler. In this case, let's talk about part A. So part A, they want to know the max height. Well, there's a couple ways you could do this. You could say, wait a second, this is height as a function of time, and they're actually asking for the maximum of that. If you're more a person that leans on your mathematical history, what way might you consider solving for the max height? What did you learn in calculus, for instance?
You find the maximum of the equation.
So how would you find the maximum of this h of t, for instance? Actually, let me look at chats because sometimes people are actually chatting the answers. Oh, there's other stuff. Okay. Remember how to find the maxima in calculus?
You take the derivative twice, and then whatever number you get, the time for that, you plug back into the original equation.
Sort of. You're mixing up the two steps, but yeah, you're on the right track. To find a maxima, you take a derivative set it equal to 0, and that gives you an extrema. That means it could be a maximum, a minimum, or a point of inflection. Then you take the second derivative, and if that second derivative is in fact positive, it's a minima. And if the second derivative is a negative, then it's a maxima. If it's 0, then it's a point of inflection. But yeah, so you're thinking along the right lines. You just sort of got a little discombobulated. So that's a mathematical way. I could just take the derivative of this, set it equal to 0, solve for t, right? And then technically I'd want to check to make sure the second derivative, since it's supposed to be a maxima, is a negative. And I think you can see that that's going to be the case, because by the time you take the second derivative, only that negative is existing. And then I would go back after I had that t and I'd plug it back in here and find out what the max height is. That's perfectly good. Now, let me show you how you would do it with regards to physics. So in the physics world, we know that as a projectile is going up, it slows down. And then when it gets to its max height, the vertical velocity is what? Slows down. What's the vertical velocity right there? It's that easy.
The minimum.
Sort of, yeah. It actually is the minimum magnitude, so yeah, it should be 0, right? So you could also find this velocity as a function of time and set that velocity equal to 0, which lo and behold is the exact same thing the math told us, right? So dr dt, which is v of t, you can already see is 30.0 meters per second I hat plus 40.0 meters per second t minus 9.80 t, or excuse me, no t on this one. T j hat. And that's just our typical V0 plus AT, right? The equation V equals V0 plus AT. That's just that, right? So now we're going to set that equal to 0. So v sub y of t equals 0. Well, that just means 40.0 meters per second minus 9.80 meters per second t is equal to 0. So clearly we see t max height, which was actually part B, so we're getting it early. That t max height is just going to be 9.80 divided by 40 divided by 9.80, which should be a little bit bigger than 4. So 40 divided by 9.8 gives me 4.08. And I'm going to keep one extra digit. And that turns out to be seconds, because meters per second divided by meters per second forces the second on top. So that's actually the answer to B, even though we weren't shooting for that yet. Now we have it. We can actually use it to find A. So for part A, we're going to say y of t max height is what we're solving for. That's actually going to be what we call h. So that's going to be 30.0 meters. Excuse me. I wrote the wrong component. That's going to be 100.0 meters plus 40.0 meters per second t, which in this case we're substituting t with 4.082 seconds, minus 4.90 meters per second times 4.082 seconds squared. And we can go ahead and compute that. I'm going to say 100 plus 40 times 4.082 minus 9.8 times 4.082 squared. And I get 99.98 meters. I should only have 3 sig figs, and when I actually round that, that becomes 100.0 meters with a line. So that's part A, actually. Any questions on that? Now, ideally, you guys should be putting in these numbers yourself just to make sure I don't make any mistakes. So always keep that in mind when I'm solving problems. It's better for you to be at least backing up my calculations. Maybe you're not taking all the notes, which I would prefer you to do, but definitely at least check my calculations. So that turns out to be pretty confident the right answer. So we've now done part A and B. Part C, yes, go for it.
So you had the max height of roughly 100. Is that 100 above the initial starting point, or?
Oh, good point. Wait a second. Did I actually add the 100? No, that should be. Yeah, that's stupid. Something happened. I'm glad you asked that. So I did get 4.08 seconds. The height should be 100 meters plus. Oh, stupid me. Damn, I did the same thing yesterday. Right here, good thing I asked you guys about this. Right here, I put in 4.90 times 4.082. But lo and behold, when I put it in my calculator, I did not use 4.98. I saw that and wrote 9.80. So yeah, you're exactly right in mentioning that. So let's correct that. I'm going to put a bold green line over it to show how angry we are. This is all right, by the way. This, however, is not right. Calculator error. I should say calculating error because it's my mistake, not the calculator's. The right answer, however, is my calculator actually allows me to go back and just erase the part that was wrong. So I'm just taking out the 9.8 and putting 4.9. I swear this is the funniest thing because I did the exact same thing yesterday when I was teaching the same class to obviously a different group of students. This comes out to be 181.63 meters. Now back to your question, which wasn't necessarily, well, maybe it was. I hope you were noticing what I hadn't put together yet, but 100 meters was exactly the height it left at. So that's problematic to begin with. In this case, it's actually because of the initial zero being y height of 0 being down here, valley all the way to the peak. So it only went an additional 81.6 meters basically above the height of the cliff. So we would call this answer for part A 182 meters to the proper number of sig figs. So thanks for asking the question. And yeah, I do scan these notes. I've been with your class, I've been doing it the same day, usually within an hour after class. So I do it every day, and you can find them all on my Google Docs link. And they're listed, as I've said before, like today's date is 09/10/21. So you do a search for that, and then you just look for your section, which I believe ours is D01B. Okay, double check me on that, because for some reason there was one that was weird, so it was like a 2 instead of a 1. But if you see that, you'll know, and if you actually look at it, you'll probably recognize it or not. Okay, so we now have part A and part B solved. For part C, they want to know the range. Well, that requires us to figure out how long it's in the air, because if I figure out how long it's in the air, I can just multiply that by 30 meters per second. And that'll tell me how far it's traveled horizontally. See how we're completely ignoring the fact that the two motions are some sense related to each other. We're just using one thing to determine one of the parameters and then plugging it in the other thing, because it's like two independent problems. One problem is a ball rolling by without friction at 30 meters per second. The other problem is a ball being shot straight up at 40 meters per second. So that's sort of the big crux of solving these types of projectile motion problems. So part C, I'm going to set y of t equal to 0. Now here's the neat thing. Well, I'll cover that in a second. Y'all know this is a quadratic formula, and it's going to give you actually 2 answers. And I'm going to explain physically what those 2 answers are. So when I do this, I'm going to say 0 is equal to 100.0 meters, hearing that little underline, plus 40.0 meters per second t, minus, here's the important number, 4.90 meters per second t squared. Okay, according to the Pythagorean theorem, according to the quadratic formula, t will equal negative b, which is negative 40.0 meters per second, plus or minus the square root of 40.0 meters per second squared, minus 4 times a, which is negative 4.90 meters per second, times c, which is 100.0 meters, divided by 2a, and a is of course negative 4.90. So 2 times that would be negative 9.80 meters per second. So you can see if this works out so I can add that, then the result on the top should be meters per second. And when I divide meters per second by meters per second, that's going to give me seconds. So I know those units work. Not only that, when I multiply this meter times this meter per second, I get meters squared per second squared, which is the same thing I get here. And when you take the square root of meters squared per second squared, you get meters per second. So that all checks. The other thing you see is this number is going to become negative, or this number is negative, and then it'll be plus or minus. This number is definitely going to be positive, and you see, because I got a negative there, we're not going to get any imaginary answers because all these things are being added. So what depends here is how big this is. So when you subtract minus subtract, that's going to be all negative divided by a negative. That would give you a positive time. When you add, however, if this number is bigger than that, then that's going to become positive on top divided by a negative. That's going to give us a negative time. So we'll keep that in mind. So now I'm going to get negative 40.0. Now I've worked out all the units. I don't need to carry them anymore. I'm just going to take and figure out what 40 squared is plus 4 times 4.90 times 100, which, you know, you can probably work that out in your head as well. So 40 squared should be 1600. And then we're going to take that and add to it 4 times 4.9 times, and I did write 4.9. I did not accidentally do 9.8 this time, times 100. And in this case, I get 3,560, and I'll take the square root. So this right here is 3,560. Notice that was 1,600, so that only went to the tens place. And this was 3 sig figs as well, and this was 3,560. So this only went to the tens place, but it had 3 sig figs. So when I take the square root of it, I should still have 3 sig figs. And that number is 59.665 or 666. So this is 59.665. And actually it rounds to 6. But 3 sig figs is all I'm supposed to have, so I'll leave that off. And then I divide that by negative 9.80. And you can see negative minus a negative, that's going to give me a negative divided by a negative. That should give me a positive. So I'm going to do that, and that should be our right answer. So I'll say negative of that answer plus negative 40. That gives me negative 99.6 or negative 99.7. I divide that by 9.8, negative, of course. And I get positive 10.16. seconds. Now, when I subtract 60, negative 60 from 40, basically I get 100, but it should be rounded to 1 decimal place. So I actually get 4 sig figs there. Then I divide by 3. So that leaves me again with just 3 sig figs. So 10.1. The other one is interesting. I'm going to go ahead and compute that. So I'm going to say negative 40 plus 59.6657, and that gives me 19.6657, positive, of course, divided by 9.8 or negative 9.8, and that's going to give me negative 2.00. Again, that turns out to be a negative plus a positive, but when you subtract 60 from 49, you get 19.66. So that really should give you 3 sig figs. So that should be 1 decimal place. This top number is 19.6 to 1 decimal place divided by 3. So that's 3 sig figs again. So really, it should be rounded to negative 2.01 seconds. Now, here's the cool part. This equation that we set up for the using the quadratic formula is really the equation for a problem that has the exact same thing, but it was the entire parabola. We're just studying the part where the parabola started right there. So you could find that the exact same problem has the same equations, and the 0 of time would be here, and lo and behold, that's exactly 2.01 seconds before that. So that's what that negative 2.01 seconds is if this projectile was fired from the ground, then after 2.01 seconds, it would be right here at y equals 100 meters x equals 0, and its velocity would now be 50 meters per second at 53.1 degrees. So that's what that negative 2.01 second means. But this is the time aloft, what I call hang time. We didn't ask for that, but we got it anyway. So it's kind of neat to know. Now that we have it, we just plug it into the x of t part of the vector, which is that. So now we get range is equal to r is equal to 30.0 meters per second times 10 point, let's call it 10.17 seconds. And 30 times 10.17 gives me 305.1 meter. And of course, that's 3 sig figs and 3 sig figs. So I really should not include that. And I'll just call that 305 meters. So that's part D, or excuse me, C. Okay, we only got like 5 minutes left. So I'm going to quickly show you how to find the final velocity. It's actually really easy because we took the derivative of the of the position versus time, which gave us the velocity vector, and we can just use that and find out what it will be at that time, 10.17 seconds. So looking up here at the velocity equation, I'm now going to say, okay, v of t hang time is equal to 30.0 meters per second I hat, which is exactly what we expected, because remember, I made the argument that basically the horizontal motion is a ball rolling at a constant speed of 30 meters per second. Now the other part is plus. Now I'm going to put in 40.0 meters per second times, I'm going to make that a square bracket, times 10.17 seconds minus 9.80 meters per second times just plain t this time. So it'd be, excuse me, there was no t on this one. Sorry about that. You got to watch out when you're doing it, because I just stole part of the x of t or y of t equation. I took that part instead of that part. That's why I had no t. Remember, I did it before there too. So one day you're going to be old just like me. No, not really. I'm sure you will be, but all right, 10.17 seconds times that, and all that will be in the j hat direction. And this literally gives me exactly the vector that I want, at least in unit vector notation. So I get obviously 30.0 meters per second I hat. And then this one's going to be 40 minus 9.80. So I made 40 minus 9.8 times 10.17. And I get negative 59.66, which I think you'll remember that number from earlier. So I get negative 59.67 meters per second in the j hat direction. So that's actually the final velocity. Now, that being said, if I give it to you in unit vector notation, I expect you to give it back to me in unit vector notation. But in this case, and in many cases, I'll ask you to give me back it in the unit, or excuse me, the magnitude direction notation. So I'm going to do that as well. So now let's draw this vector as it really is. So this vector is in XY space, and it has a x component of 30 meters per second. and it has a y component of basically -60, so about twice as long. Okay, so what I want to find out is what is this angle phi and what is this magnitude v final equals question mark. Well, phi is equal to the tangent inverse of, notice I'm leaving out the signs, 59.67 meters per second over 30.0 meters per second. I'm going to take tangent inverse, 59.67 divided by 4, or excuse me, divided by 30. And that gives me 63.31 degrees. And notice that's below the x-axis. So if I wanted to specify that, that's actually standard notation. So I could just write at -63.3 degrees, because by writing it negative, we know it's supposed to go clockwise from the positive x-axis. And then V final magnitude is just V final. That's going to be given by the Pythagorean theorem, which is 30.0 meters per second squared plus 59. Notice I didn't care about the negative because I'm going to square it anyways. Meters per second squared square root, and I get V final is equal to 30 squared plus 59.67 squared. And then I take the square root of that, and I get 66.78 meters per second. That's one extra sig fig, of course. And that's my final velocity. And that truly is D. Now I should think about those units. 30 squared is actually 900, and that allows up to the ones place. 59.67 with 3 sig figs squared is 2,467.109, but that's only 3 sig figs, so that only goes to the tens place. So when I add those two, I only get to the tens place, but that's still 3 sig figs. Take the square root of that, that gives me 3 sig figs. So yeah, that works. Okay. Sorry about all that. I just want to make sure I'm teaching you proper significant digit rules, and you got to, whenever you're adding or subtracting, things get a little dicey, so you got to play with it. Your actually time is up. You guys are free to go, but I'm also here to answer any questions if you have any more. I have a lab this afternoon at 1, I believe it's 1. Anyways, that's another time. I've told you guys can come get help if you want to. And some of you might actually have the lab with me. So any questions, anyone?
Yeah, I had a question, a couple like questions about personal attendance.
Uh-huh.
So last lab, I had really spotty internet connection, and I went in and I told you, and you're like, that's fine, and I kept on getting kicked out, and I didn't get credit for the attendance on the lab.
Gotcha.
I
And you
was
were in my
gonna
lab
try-
yesterday? I remember you coming and talking to me.
No, this is Friday. It's a Friday lab.
Okay, Friday.
Yeah.
Gotcha.
So
I do remember you coming and telling me you were having spotty connection. I'll give you back those 50 points.
All right, thank you. I also have one more
No
question.
problem.
So
Yeah, go for it.
I'm part of this thing called like the ambassador program at TCC, and basically so we have a mandatory meeting that's happens to be at the same time as the lab today.
Okay.
Will I be penalized if I miss that lab or no, or what?
Yeah, you'll lose that 50 points of attendance, but if you still do the lab like on your own, or maybe hook up with partners later and get them to help you through it, you can get the other 50 and the lab grade back. And remember, I do drop one lowest lab grade, and also, of course, allow you one miss and one late turn in. So it wouldn't affect your grade to miss today. If you knew that, that would have been better for you to try to attend one of yesterday's labs or the day, one of the Wednesday labs. That's why I sent everybody out those links to those. So always keep that in mind. We're essentially doing the same lab every week, but if I remember correctly, the Friday lab is 1 week behind. So yours actually would be, yeah, yours wouldn't help because you would do next week's lab if you would have went yesterday or the day before. So there was really nothing you can do to help. But like I said, you can do that, turn it in and get 50% of the attendance points, and then 100% up to 100% for the lab credit. Okay.
Okay. All right. Thank you.
No problem. Anybody else? Yes, this will be posted probably in the next 15 minutes or so. So I will go ahead and let you guys go. It doesn't seem anyone else has any questions, so I'm going to go ahead and call an end to it. If you still have a question, but your speaker's not working, then text me, chat real quick. Otherwise, I'm going to end the meeting. All right, I'll go ahead and end it. See you folks. Have a good one.
Sir.
Yes.
I just wanted
Yes.
to say I showed up quite late today. I'm not really sure why I thought that the class was noon to 1, but I showed up like
That's happened
10.
to me before. I was wondering. I was like, Gavin's always here on time.
Yeah,
the good
I
news
just
is
wanted,
the video will
to
be
apologize
posted
on that.
probably
And
in an
yeah,
hour or two.
give that a look as soon as you throw it up there. So thank you for your
Not
time.
only that,
anyways.
I gave you access to the one I did in another class, which is an entirely different projectile motion problem. So you can watch the other one now, even though this one won't be up for another hour. Okay.
Oh,
And
okay.
the notes are available for that one too. I even put the date on it in the names. It's a YouTube video, but in the description it says the date, so you can do a search for that and find the actual document for it too.
Yeah, let me
Okay.
let me take a look at that actually. Excuse me. So your YouTube videos has like most of what you cover, or like are you just posting
It's
that in
got
the
a
little
lot of
modules
problems.
list?
It's got a lot of the full lectures, which are really longer than most people want. But it also has some ones where I just isolate and look for certain problems. So I'll solve a projectile motion problem, or I'll solve a kinematics equation or a Newton's second law equation. It's got all those up there as well. There's a list of the titles, and the titles are descriptive enough, I think, for you to figure out what it is. I put that up in the important documents page where the YouTube link is as well, so you can look at that for titles.
Okay. Is this September 9 lecture on vectors? Is that the one you're talking about?
Yeah, that's the one.
Gotcha. All right. So
Yeah, there's a
I'll
9-9 one on vectors, and I think it's the projectiles with vectors or something like that.
yeah, I mean it just says vectors, but it's probably in there. And then this one for today is going to be uploaded into that same section for week 3, or is that going to be somewhere else?
I usually first, because it's quicker, I first put it on as a studio file in your weekly module for your lecture, and I'll later put it on the actual on the actual YouTube channel.
Okay, so usually Canvas first and then YouTube later. Gotcha. Okay, thanks again.